So in the previous class, we discussed about the second order circuits, started with source-free response of series RLC circuit. Right. So from series RLC circuit, so we developed a differential equation. The differential equation has two roots. So based on the nature of the roots, we had three solutions. So one is the overdamped case, underdamped case, and the critically damped case. Right. So here, if you summarize the solutions, so we have this is for underdamped case. In case of, right, so what we have for overdamped case, so e to the power of plus S1, A1 into e to the power of S1t plus A2 into e to the power of S2t. So in case of critically damped, so that is I of t, which is equal to, so what is the critically damped case? What is the solution for critically damped case?
The A1t plus A2 whole into e power minus alpha t.
A1t plus A2 into e to the power of minus alpha t. Correct? Right. So these things are so based on their roots. Right. So here the roots are same. So here the roots are real and negative, and whereas here the roots are complex. Right. So if you observe these, right, so how exactly these waveforms look like? So that means, so we have this. So this is the current response for particular current I of t. So assume that its initial conditions are same. Assume that the initial conditions are same. So only the difference is the resistance, right? So why this response is like this? So this is because of the resistance in the circuit. Okay. So resistance, so absorb the energy stored in capacitor as well as energy stored in inductor. So we have three kind of responses. So this is related to overdamped. So this is damped response. So this is shape of current. So this is critically damped. And this is underdamped. So for all these three, right? So if you assume that, so this is oscillatory, so that means it is varying with some frequency. So this frequency or this time period, which is equal to 2 pi by omega d. So what is omega d? What is omega d? What is omega d? Damping frequency. What is its value?
So under root omega naught whole square minus alpha square.
Minus alpha square, right? So which is varying with, so this frequency, right? So let us assume that, so we'll talk about first this case. So let us assume that if R equal to 0, if R equal to 0, right? So what is the value of omega d? So what is alpha here? Alpha, what is alpha value?
0.
Alpha is R by 2L, right?
Yes, sir.
So this is equal to 0. So that means omega d equal to square root omega naught square. So that means omega naught square. So that is equal to omega naught. Right. So this R is causing the damping. So what is the meaning of damping is, right? So what is the meaning of damping? So it is the gradual loss of initial stored energy. So damping means gradual loss of initial stored energy. So here, so the current, how this current is behaving. So starting from 0, suddenly it reaches some peak value and it is dies to 0 gradually. So in this case, so this is also same, and it is reaches its peak value. For example, in this particularly for critically damped case, so it reaches its peak value at 1 by alpha. For time period equal to 1 by alpha, it reaches its peak value. Similarly here, in the third case, so it is an oscillatory response. So that means it's under damped response. So it is why it is oscillatory, because it contains the cos and sine terms. If you observe the solution, it is consists of cos and sine terms, right? So that's why it is oscillatory, or that's why it is varying sinusoidally or cosinusoidally. So here this is starting from here, here. So slowly, gradually it reaches to 0. So whatever the stored energy is there in inductor and the stored energy in the capacitor, so slowly dies into 0. And that is absorbed by the resistor. That is absorbed by the resistor. If the resistor is not there, so that means there is no damping. If resistor is not there, so there is no damping. So that is known as undamped. That is known as undamped. So here, so omega d equal to omega naught. So how it will behave? So how this waveform will behave now? Will it reduce to 0?
No, sir.
No, sir.
No, sir. Constant
Consists of
amplitude.
only inductor and capacitor, right? So energy stored in inductor is dissipated, or it will transfer to capacitor, and energy stored in capacitor is transferred to inductor. So that means the response will be oscillatory. It will be like this. And what is its time period? Right, its time period is 2 pi by omega naught. Its time period is 2 pi by omega naught. So that is known as undamped response. So that is known as undamped response. Right. So that means a pure sine wave or a pure cos wave. Yes.
Sir, in all the three figures, sir, that dotted line, sir, what does it represent?
Which one?
Sir, in all
These
the three
dotted.
figures, that dotted line, yes, sir.
So this indicates the peak value. Okay. So when exactly it touches the peak value, that indicates. So here this dotted line is, this indicates the peak value. Okay. Right. So here also,
And sir, in the
moving across the
overdamped one,
dotted. So if you notice that this is e to the power of minus t, okay, that is the one. It is minus of e to the power of minus t. So it is varying from e to the power of minus t to e to the power of minus t. Okay. Right. So where we are, yeah. So that is known as undamping, right? So that will never reach to 0. So but practically, so you will not get this condition. So practically you will not get condition. So always some finite value will are wedges. So that is associated with inductor or capacitor. Of course, both is some resistance. So therefore, most of the cases, it may be like this or like this or like this, depending on the damping ratio, depending on the damping ratio zeta. All right. So here, the first thing is overdamped. So overdamped case, so it will reach the longest time. So among all these three, if your initial conditions are same, it will reach the, or it will need longest time to reach the steady state, or reach the steady state value or the final value. So in this particular case, the final value is 0. It requires longest time. So whereas here, so it requires shortest time. It requires shortest time to reach steady state. So this is medium. So that means this is between, it is neither longest or not shortest. So this is intermediate. So it is intermediate case. Right. So overdamped
sir, in
requires
case of
longest.
undamped, it will be infinity.
No, it will reach to 0. Okay. So
No, sir,
here,
undamped, sir.
no.
Sir, in case of undamped. Sir,
So
in
that
case
we are
of
discussing
undamped, sir,
practical steady state value. See, in one of the class we discussed it, right? 5 time constant. So here that practically you will get 0 value. Okay. So let us assume that, so this is 1000 volts. Okay, so say for example in few cycles it is reached 2 volts. So what you will say? So practically it reached steady state, right? Okay, so obviously theoretically it required for any case, so theoretically it required infinite time, but practically it required some finite time, right? It may be a close value. Usually 1% or 2% approximation is, for example, you have 1000 volts is the peak value. So usually say the 10 volts. So that is fine. Okay. So 10 volts, we have treated this as 0. Okay. So ideally, it require infinite time, but practically it require, we already seen that when you're defining the time constant, so after 5 time constant, the value is practically 0, that is somewhere around 0.04% only. So that means practically we treat that as 0 volts or 0 amperes current. Okay. So here if you compare that, if the initial conditions are same for all cases and L and C values are same, so only thing we are changing is the resistance. Based on the resistance only, right, it may be over damped, under damped, or critically damped. So here over damped requires longest time to settle, so, right, critically damped so requires shortest time to settle. So whereas this under damped requires some intermediate time. So in fact this critically damped is the boundary line between, so this critically damped case is the boundary line between over damped and under damped case. So this critically damped case is the boundary line between over damped and under damped case. All right. So if you go on over damped side, so the response will be this. So practically, right. So practically we cannot actually see, or we cannot actually say that this is over damped or this is critically damped, right? So it look like both are same. Look like both are same. So the only difference is, the only way, so we can say that whether it is under damped or critical, whether it is over damped or it is critically damped. So that is at the in case of critically damped, its peak value we can obtain, or its peak value of the response that is achieved at 1 by alpha time. So at 1 by alpha seconds, so it reaches its peak value. All right. Okay. So here, so this especially another point, so especially this kind of nature, so this is known as ringing. So this kind of nature is known as ringing. This kind of nature is known as ringing. So applications for the second order circuits, we have a lot of applications. So for this second order circuit, so especially we use in discharge lights. So applications for this one, so we use in discharge lights, photo discharge lights, right? So in automobile, spark plugs, automobile, spark plugs, actuators, and in applications like where we require actuator, for example, actuator especially in car airbags or something like this. So all these things, so these things are used, right? So exactly at what condition we use this? So most of the cases we use this under damped response only. So most of the case, or when we are designing a circuit, so we use the under damped response only. We use under damped response only. So why? Because it's the critically damped response that gives you the least settling time. The thing is that it's difficult to achieve, right? If something is gone wrong, so it will move to the other zone, right? It will move to the over damped zone, right? So we have some safe limits. So that's why most of the cases we use this under damped case. So some of the applications are power electronic circuits. Power electronic circuits, almost all power electronic circuits, we use these second order circuits. Right. So why exactly it is useful? So why exactly it is useful? right? So here, so if you solve some more problems, you will understand that. The thing is that, so if you operate this second order circuits, so you will get a large voltage here, even though, for example, your source is 12 volts, right? So you may get a voltage which is equal to, for example, 2000 volts you will obtain. So with this, a large voltage is obtained for a brief period of time. Large voltage or large current is obtained for a brief period of time. Okay. So if your applications, for example, you require, for example, photo lights. So photo lights are usually operate for brief period of time, right? So maybe in the order of milliseconds, or at most you have 1 second in the range, right? So when the photo is clicked, so nearby, so there are some infrared sensors. The infrared sensors detect that photo is capturing, so that it eliminates it illuminates. Okay. So during that time, so we have some LED lights are there. So here what we have to do is we need to inject, or we need to forcefully, or we need to supply, or we need to provide a large current across those LED lights, so they will glow brighter. They will glow brighter, so it will illuminate more light. So that's how it will work. And that period is also a brief period of time. So in the order of milliseconds, or at most we have 1 second. So another application is a spark plug. So another application is spark plug, right? So why spark plug is used in automobiles, especially two-wheelers or four-wheelers? Why the spark plug is used? You're aware of the spark plug, right? So this is especially, you can see the two-wheelers. This is for ignition, right? Okay. So in actually what we have, so we have in combustion chamber of this automobile, if you have 4-stroke engine or 2-stroke engine in the combustion chamber, so this air and the petrol is both mixed, right? So air and petrol, so both mixed. Somehow we need to fire that. So to fire that, so you require some high voltage. So that how that high voltage is obtained. So we have some sparks, we have some plugs here. So here some circuit will be there. Okay. Right. Here some two terminals will be there, or two electrodes will be there. So between these two electrodes, so there will be some gap. Some air gap will be there between these two. So what we have to do is we are using some second order circuit, and we'll provide high voltage across these two gaps. Between these two gaps, we'll provide high voltage, right? So whenever we have high voltage is there, so here this is the gap between, this is one electrode and this is the other one, right? So assume that this is gap is there, so, and we are providing some voltage, for example, in the voltage of 200 volts. Okay. So what will happen? So here nearby the air is there, right? So this air will start ionizing. The air is start ionizing with this high voltage, and it will be a spark will appear. A fire spark will appear across these two terminals, or a spark will occur across this air gap. Okay. So why exactly the spark will appear, and how this ionization is done? So you will that will be discussed in a later point of your courses, other courses. Okay. The thing is that, so here if the gap is there, if we provide a high voltage, so for high voltage, so there is ionization of this air will happen. So during that ionization, so these two terminals will be short circuit for a brief period of time. So with that short circuit, so it will produce a spark, and the spark is used to ignite the air and fuel mixture in the combustion chamber. All right. So that is one example. That is one example of this spark plugs in automobile. And actuators means if you want to, if something is detected, something wrong is detected, and if you want to activate something, or if you want to close a particular switch, or if you want to operate a particular thing. For example, if you consider an example, if you have automobiles where airbags is there, right? So whenever a crash is detected, it's supposed to be open immediately, right? Supposed to be open immediately. The time period is usually in the order of milliseconds, right? So here to activate this one, so to activate these airbags, so these second order circuits are used. So whenever the crash is there, right, the circuit is closed, and the particular circuit is closed, and the same phenomena, a high voltage appears across the switch. A high voltage is appear across the particular switch, so where it will activate the airbags. Right. Now the switch is closed. So now the switch is closed. So now the airbags are in operating conditions. Right. So in power electronic circuits, so power electronic circuits is basically turning on voltage or turning off voltage. That means switching operation is basically right. So in that circuits also, so we use these second order circuits. So at this point of time, so you may not aware of this power electronics and other. The thing is that so we use this as a second order circuits, especially in this power electronic circuits. Okay. So these are the some of the applications of these first second order circuits. Some cases we use on first order circuits, especially these first order circuits are used in delay circuits. If some time delay is required, so we normally use RC circuit. So RC circuit will provide some time delay, right? So the same time delay if required, so that circuits we use normally use these circuits. Okay. For simple example of a time delay circuit, it will be something like this. Simple example of time delay circuit. You have some pulses there. Okay. So you have some pulses there, right? You want to delay this pulse by, for example, 1 second. You want to delay this pulse by 1 second. Right. So let's say it is 5 volts. So how to delay this pulse? So how to delay this pulse? So whatever this pulse is there, this is the input to the pulse. So this is connected to a RC circuit, right? So this RC circuit is having some time constant, right? So this RC circuit is having some time constant. If this is the pulse is given, this is the pulse is given. So on the other side, so how this pulses look like? So this is voltage, right? So how this pulse is vary in this particular case? How this pulse is delayed, right? So here, so it is excited by 5 volts. So that means this is delayed here. Agree? Or agree with this? This pulse is delayed here and it is moving like this and it will be, okay. So this is the response of RC circuit. If this is the circuit. So this is the original pulse. The red one is the original one. And this one is the delayed pulse. Understood? So this RC is causing some time delay. RC is causing some time delay, right? So usually, for example, if you are integrated circuits, if you are studied that AND gate, NOT gate, you have completed digital electronics course. Okay. So usually different gate circuits are there, right? So usually it will operate for 5 volts. Okay. So that means if it's usually this is supposed to be 5 volts and these are somewhere around 3.3 volts. For example, IC integrated circuits are used. So usually that is operating for, usually they are operated 5 volts, for example, but they start operating from 3.3 volts onwards, right? So that means this pulse is, that is delayed by some portion of time. This pulse, this particular pulse is delayed by some portion of time, so which is equal to when its value reaches 3.3 volts, so then it is start operating. Okay. So this is how these delay circuits are working. Okay. So you may not understand at this particular point of time, so but you will definitely understand. So once your course progresses. So we'll try to solve some problems. So initially the switch is at position A. Initially this position A for a long period, and it is moved to position B at t equal to 0. At t equal to 0, right? So for this particular circuit, so find out the voltage across, or find out the response t greater than or equal to 0. So capacitor voltage for t greater than 0. Okay, right? If this is the case, so how to start this one? So first we need to find the initial conditions, right? First we need to find the initial conditions. So if we assume this is the current I, so inductor current I, so I of 0, what is I of 0? So what is I of 0? So initially the switch is at position A, right? So what is I of 0? So how this circuit will behave? So this capacitor is open circuited and this is short circuited, right? So what is the current through this inductor?
0 amperes.
0 amperes, right? So this 0 amperes. So now tell me what is voltage across inductor or voltage across capacitor?
20 volt.
So this 4
20 volts.
amperes, this is open circuited, right? Whatever, this is also 5 amperes. So 5 into 4, so that is 20 volts. Okay. All right.
Yes, sir.
Okay. So what is the next step? So when the switch is closed, the circuit will be modified like this. When the switch is closed, circuit will be modified like this: 20 ohm. This is 0.25 Henry, and this is 0.04 farad, and this is the current I, and this is the voltage V. Okay. All right. So what is
Sir.
the next step? Yes. What is the next step? So we have RLC circuit is there. So first step is we need to find the roots for this RLC circuit. So based on that, so we need to choose one solution. So based on that, we need to choose one solution, right? So how to find the roots? For finding out the roots, we need to calculate the alpha value and omega net value, right? So what is alpha value? What is alpha? Alpha is R by 2L, right? So what is R by 2L?
20.
20. What is omega naught? What is omega naught?
10.
Omega naught is 10.
Yes, sir.
10, right?
Yes, sir.
So here, we, under in which case it is coming?
Sir.
So it is over damped case, under damped case, or critically damped case.
Over.
So here alpha is greater
Overdamped.
than omega naught, right? So it comes under over damped case, right? If this is over damped case, so what will be the response of I of t? So how the I of t will look? It will be
A1 into e power minus S1.
a1 into e to the power of s1t plus a2 into e
A2
to the
into
power of
e power
s2t.
S2t.
So what is S1 and S2 values? What is S1 and S2?
Minus alpha plus minus square root alpha square minus
So
omega.
find out. So what is S1 and S2 values?
Sir, minus 20 plus minus under root 300.
What is the value? If you solve this one, so you will get 2.679. So that is one root. and another root is minus 37.32. Okay, so that means the solution will be I of t equal to a1 into e to the power of minus 2679 t plus a2 into e to the power of minus 37.32 t. Okay, so this is the one, right? Understood. So our objective is to find this a1 a2. Our objective is to find the a1 a2. So if you go back, so we know that I of 0 equal to 0 amperes, right? So that is one initial condition. So I of 0 equal to 0 amperes. So if you substitute that one, so what you will get? So substitute t equal to 0. So a1 plus a2 equal to 0 volts or 0 amperes, right? a1 plus a2 equal to 0. All right. Right, so this is itself not enough to find a1 a2, so we required one more initial value, right? So how to get another initial value?
Voltage across inductor.
So this one.
Voltage across capacitor.
So this one. So you know only the current, right? You only the current one, you know, right? You know only I of t, not V of t, right? If you
Yes,
consider
sir.
voltage across capacitors, so that will become complex, right? You know I of t value, right? If we bring this one on the other side, so what is d I of 0 by dt? So what is di of 0 by dt? It's minus 1 by L R into I naught plus V naught. So what is this value? It's minus 1 by 0.25. R is 10, right? 10 into I naught is 0 plus V naught is 20. So what is this value? Minus 80? Minus 80 ampere per second, right? Is this
Yes,
right?
sir.
Thing is that, so differentiate this one with respect to t and substitute t equal to 0. Understood? So that means di of 0 by dt, right? In other words, di of t equal to 0. So tell me what is, if you differentiate this one, what you will get? So it will be minus 2.679 into e to the power of, sorry, a1 into e to the power of minus 2.679 t, right, minus 37.32 e to the power of a2 into e to the power of minus 37.32 t. Agree? This is the one, right? So we need to substitute t equal to 0. In this we need to substitute t equal to 0. If we substitute t equal to 0, it is 2.679 a1 minus 37.32 a2. So which is equal to, what is its value?
minus 80
Minus
ampere per
80,
second.
right? So this is equal to minus 80. So this is one equation and this is another equation. So we need to solve 1 and 2 for a1, a2.
So 2 and minus 2.
2 and
Sir, A2 is 2.309.
a2 is 2.309 and a1
Minus
Minus
2.309, sir.
minus 2.309. Right. So therefore overall solution, so how this overall solution will be I of t equal to, so what is a1 minus, okay, or we will alter this one, so one is minus, right? So 2.309. So second term, what is second term? E to the power of minus 37.3 t minus e to the power of minus 2.679 t. Agree? Understood?
Yes, sir.
Right. So what is the next step? So this is the not one. This is the this is not the one they asked, right? What is the next step? We
P
have
of
to find voltage across this capacitor, right? So now how to find voltage across capacitor V of t? How to find voltage across capacitor if you know the current?
Sir, integration IDT by
So
capacitance.
we'll
Right. This will
integrate.
be I1 by C integration of, okay, integration of
IDT.
I dt into dt, right? So now tell me what are the limits?
0 to T, sir.
0 to t. If you are using that 0 to t, so that means you are no longer considering the capacitor voltage, right?
Yes, sir. Initially it is 20, sir.
So how to add the 20? So that will be plus 20. Agree? In other words, so it will be minus infinite. So here no more 20 here. So that means if you need make it 0 here and its initial value is 20. This 20 equal to integration of minus infinite to 0 I of t dt. So 1 by c. Understood? So why this minus 20? This is from initial conditions. Okay. So find out its derivation, its integration. Yeah. What is the answer?
Sir,
Yeah.
sir, approximately it is coming e power minus 2.679 t upon 2.679 minus e power minus 37.32 t upon 37.32.
Just a second. So you will get approximately, I have answer, 21.55 e to the power of minus 22.679 t minus 1.55 e to the power of minus 37.32 t. Is this correct?
Sir, we need to add 20 also, no, sir.
We need to add the 20, right? If you add 20, what you will get? For 20 related.
19,
Sir, 20 is getting
1999.6.
cancelled, sir.
20 is getting
It will
cancelled.
be 0.0121, sir.
I think 20 will be cancelled, I think.
Yes, sir,
Yes, sir, it will
20
be
is getting
20
cancelled.
will be cancelled. Okay. So why it is cancelled means when you are writing the differential equation in the beginning, right? We consider 20 also, right? So that's why it is cancelled. Okay. So this is the solution. So for this particular case. So try to solve this problem. .5 Henry, and this is 1 millifarad, and this is 60 ohm, and this is 40 ohm, and this is 10 ohm, and this is 30 volts, and this switch is open at t equal to 0. Okay. So calculate I of t for t greater than or equal to 0.
Sir, what do we need to find?
I of t, inductor or capacitor current, inductor current. Actually. So here I of t you will get answer minus 9.6 t into e to the power of minus 20 t. This is the solution. It seems like it is critically damped case. Okay. It seems like critically damped case. So we'll stop here, and in next class we'll discuss some more things.